Mr. Morelos, for the presentation, and floor is yours.
Thank you. So I hope everybody can hear me well. Just a bit of background. I don't know if everyone knows Lloyd's Register, but we're a 258-year-old company trying to reinvent itself, trying to keep up with the times. And I think, we've got a pretty successful track record of doing just that from, back in the day when the ships had sails to using different propulsion, steam propulsion, coal, oil. Obviously, right now we're operating in different industries. I'm part of the marine and offshore vertical. So about 2 or 3 years ago, LR realized that in any industry that we operate, there's going to be 2 very, very important things, right? On top of that list is increasing automation, and we could discuss the semantics of that quite widely if it's automation or autonomous. But the other thing is really health management. Health management is an enabler, not just for making consistent profits, having reliability, keeping uptime, keeping assets safe, but it's an important enabler of autonomy. You cannot have an autonomous system that has a long endurance, that's able to do a lot of things without it understanding what's going on in terms of its health, right? So here, I'm talking about a service that we're going to be launching sometime this year, 3rd quarter this year, which is really providing an independent review of diagnostics and prognostics. Now, this service is end-to-end. It involves, the usual stuff, which is design review, development, testing, but it also has a true life component, which is very, very important. And I hope to tackle that in a few slides. So essentially, what are diagnostics and prognostics? Diagnostics, if you think about 2 words that you're going to take away from there, diagnostics is a health meter, right? It's not a single sensor. Right? Or it's not even a few sensors, right? You cannot tell the health of something with a few sensors because some of the failure modes quite frankly, are hidden, right? They could only be detected indirectly with some form of abstraction to be able to say this is the health of that something. Prognostics is even harder, right? It involves a lot of forward projection of what the stressors are doing to the health of that something. So think of it, prognostics as a future health meter. Now, these 2 things, as I've said, it involves the right mix of different technologies. That's hardware, sensor networking devices, computing devices. That's software to manage these devices, right? To initiate some rules, some logic in the devices, some intelligence, all right? Intelligence in the sense that could you really detect, isolate, and articulate or diagnose the condition of that health? But more importantly, it also involves a human element. It's no good having fantastic diagnostics and prognostics if you cannot communicate that effectively to the people who are going to make use of that information or insight, right? So this is just like an arbitrary, not arbitrary, but this is an illustration of the useful life or the health of that something in the time. And you could, I'm sure you've seen a few illustrations like this that talks about this subject in different ways. So everything starts out new or relatively new. It might have some flaws or some imperfections in it. At some point on that life of that particular component, in this case a structure, a fault is going to be detected. That fault could be corrosion. That fault could be a highly stressed area cracking. And of course that fault being detected there and isolated, that fault does not behave itself, right? So that fault does not stop, right? That fault, the only thing it's going to do is grow bigger, stay still, if you're not using the asset, or pretty much accelerate into something that we don't like this, right? So right now, reliability engineering is based really on more on statistics of what average looks like, right? We've got, average life estimation or operational hours or cycles, what you want to call it, for different life-limited parts, right? And it's no different for structures. So for structures like the convention, at least in marine and offshore, is like, oh, we gotta lift the vessel or the asset out of the water every 5 years because, the general heuristics of corrosions and asset integrity revolve within that 5-year period. But with manual inspection, right? Although we've got trained subject matter experts with lots of experience, there's always going to be a bit of subjectiveness to it. There's always going to be that little nook or cranny in a massive asset that's 400 meters long that you are going to miss, right? So what we're saying here is this technology, diagnostics, that again encompasses a lot of elements, hopes to be accurate in detecting and articulating that fault. Because that asset operating in a particular environment, right, we don't know what those stressors are, right, in the future. We could only estimate them. So if adverse stressors, and that means, literally running your ship through storms, or, not taking of that crack that's propagating, endangering a critical aspect of the structure is not mitigated or remediated, we could have this, right? Or if we really understand these different stressors, the operating environment, with a fault detected and diagnosed, we could better manage the availability and the reliability of that assets, right? So why do we use diagnostics and prognostics? This is a simplified view of a simple rotating equipment, right? You look at the maintenance manual or the troubleshooting guide, you look at a main symptom, it says high vibration. And now this equipment might even actually have analog instrumentation, as most are as most are small rotating equipment in the marine and offshore. But what you see here is the true nature of the failure mode, right? High vibration is a symptom that leads to a particular failure mode. What you see here is that most failure modes or reality is indeed multi-physics, right? There's an element of geometrical loss that's coming out from, more conventional wear and degradation. There's a chemical element on it if, your lube oil was contaminated or it's not maintaining the right, chemical properties to it. There's an element of dynamics to it. Obviously, if something is misaligned and if it's a high-speed rotating, equipment, it's going to be reflected there. And there's also an element of, what is the fluid being passed there or what is the objective of that machinery. So a single symptom can easily lead to multiple fault modes, failure paucities, and obviously solutions or mitigations, right? So this is essentially what the technology is trying to address, and this is what Lloyd's Register hopes to provide an independent review of how effectively it really does that. So a lot of the people presenting this morning have talked a lot about this, those benefits, and every as-a-service business model is essentially reliant, and I think the good professor discussed that this morning. It's reliant on having strong diagnostics capability. Forget about prognostics, right? Because prognostics is, it's obviously more beneficial than diagnostics, but if you want to do as a service, if you're a manufacturer or even a service provider, you got to have diagnostics as an enabling technology, right? For the people on the ground, for the maintenance engineer, the technicians, and what have you, we were talking to some ship operators or even some factory owners, and what their maintenance engineers and crew essentially do on a day-to-day basis is fight fires, right? There's always something, on a typical 50 megawatt asset, always something failing on a daily basis, right? The crew are stretched out and trying to figure out what is exactly going wrong. So what they do, really, if you look at the previous slide, is you tend to do a lot of over maintenance, right? Someone told me that there's only 2 maintenance being done in most assets today because we don't really understand its health. It's either you're reacting to maintenance or you're waiting for some failure event to happen before you do maintenance, or more likely, you're doing a lot of over maintenance. And you can see that the more specific, the more granular this technology is, the better it is for the guys on the field. So if it's better for the guys on the field, that benefit gets reflected across the entire spectrum of the organization. It's good for the plant or asset manager, because now he's going to be able to understand what spares to order in advance, minimize the spares, because if some failure modes don't appear that often, why do you keep storing that spares, right? And all in all, it provides logistics efficiencies. Believe it or not, some of our clients, our big clients, carry an inventory of $400 million in spares, right? Sitting on their warehouses, right? And some of them basically, if it's got like a life storage limitation, they just replace them without even using them on the machines, right? So that is, again, that reflects back obviously to the financial viability of that operation. for us, for a company like Lloyd's Register, what we really want, why we're promoting this technology and why we're providing services to say that it's safe for use is because it increases asset safety. And our mission as a company is obviously to try to eliminate catastrophic failures in all the different industries that we serve in. Right? Associated with that, for insurers, it's an enabler for being more accurate on the actuarial science involved in the pricing of risk. So this is indeed a game changer. And of course, we're not saying that failures are never going to happen if you have this technology. I mean, this technology is great, but there's obviously a lot of room for improvement moving forward in the future. So for insurers, it also provides a very, very objective evidence for doing the claims, right? And obviously, alongside that, insurance premiums are going to be better. So where are we today? Right? The reality today is that while there are some applications of diagnostics and prognostics, there's sufficient confidence of them, but a lot of things are still done by manual periodic inspection and survey, right? We haven't, and the perspective from Lloyd's is it's not going to be like an automatic flip, like, oh wow, we've got artificial intelligence, just go jump right into it. Our role again is to provide an independent, a legible, transparent metrics on how this technology can be adopted. So gradually the confidence in application of the technology in different assets types and different equipment and different structures mature, and alongside that the confidence or the wide acceptance of the technology matures alongside it. So we're not saying you're going to be completely eliminating periodic manual inspection, because you just can't, right? Some of these things you cannot even directly, as I've said, you cannot even directly sense them. You cannot create abstracted models to say what the faults really are. So, periodic manual inspection, it need not be done by humans, but obviously, there's new technology there as well. It's still going to be a mainstay that sort of complements the confidence in the diagnostics and prognostics technology. So what's the main reason for validating diagnostics and prognostics? We're really looking for three things, right, that we hope never happens when you're deploying this technology. Those are false positives, which are an irritation, right? If you keep throwing up false alarms, people at some point will not believe them, right? But more importantly, we want to capture its limitations in terms of false negatives or missed alarms, right? Because some of these missed alarms, depending on what failure mode you're talking about, could really escalate easily to something quite catastrophic. But also, we want to make sure that when people are claiming, oh, we're able to predict this in advance in this much time, we want to make sure that that horizon is actually accurate, that there's basis, engineering or scientific basis behind that claim, right? But in reality, if you've got even a small rotating device or an asset, you've got a big list of fault and failure modes, right? The reality of that is sometimes we haven't even captured in description all of that failure modes and techniques like the failure modes and effects and criticality analysis, right? You always got to leave room for that you may not have captured all the failure modes. And within the faults and failure modes in a FMICA, if it's a complex machinery, it could be like multiple hundreds of lines, right? You got to come quite clean to the fact that not all of those are going to be diagnosable instantly, right? Some of the critical failure modes you can diagnose, but you gotta come clean that even some of the critical failure modes you just don't have the capability right now to diagnose them, right? And again, a small subset of those diagnosable failure modes will be predictable, right? So we want to make sure that whatever is the state of the technology being installed on the asset, we want to make sure that the claims on the diagnosable and prognosable failure mode stays as it is, and it stays under a wide variety of different conditions. So what is the LR approach? I'll just quickly go through this. So it basically has three pillars: confidence in the analytics, development, and testing. So these are your fault detection techniques. These are your descriptors. These are your features being used. These are the diagnostic and prognostic reasoners, right? But also, this is good, right? But that can't exist in isolation. It has to be complemented by a certain resiliency in the system installed that takes data and processes that data to create these insights or meaningful diagnosis and prognosis in the system. So cyber resiliency is not just cybersecurity. Cybersecurity is a big part of that. but it involves, basic hardware, basic software, resiliency of the network installed, and, alongside that, that's being done in a risk-based approach. But what we really want to be offering as an independent viewpoint is in the true life performance of that, solution, right? We want to make sure that false positives, especially false negatives, are actually captured and are accurately tracked such that the analytics could be in a continuous improvement through the life of the deployment of that asset. So when we say confidence in the analytics, what does that exactly mean, right? It starts with the asset or the machine, right? And then within that asset or that machine, that's a small pump, by the way, it's defining the taxonomy of parts within that asset on what you could accurately monitor. And after you've got a good grasp of what the taxonomy of the parts in that machine is, it's really subjecting it to the more traditional, risk methods or approaches. And one of them is a FMICA. It's essentially listing the different failure modes, how they came about, how you're detecting them, and how bad is bad, right? Some of the failure modes could be critical, meaning they've got a serious consequence and they happen quite a lot in the past. So you got to focus on those, right? So the critical failure modes in our review, in our assessment approach, takes a lot of importance, right? So after you've identified all the failure modes, involves that parts within that equipment, you got to be able to articulate better the failure physics. As I've said, the failure physics, sometimes it's not straightforward, but sometimes it is. Sometimes it could be just a dynamics issue. Sometimes it could be just a lubrication issue. Sometimes it could be just a thermal issue. But to say that, hey, we could repeatedly, consistently, and robustly diagnose or prognose something, you got to be able to articulate that physics of failure. Right, so obviously after articulating the failure physics, now you're going to come up with a decision like, do we have the right sensors installed? And most of the time, you probably have the right sensors installed, but sometimes you've got a missing sensor in the right place, right, with the right sampling frequency, and that's very, very important too. And obviously, at the very, very low level, we want good signals coming from the sensors, meaning, it's no good having sensors drift all the time without you understanding it because garbage in, garbage out, right? In the higher analytical models, right? So here we're talking about what are the techniques that you guys are employing to remove interference or noise, amplify the true signal, but more importantly say that this sensor piece that is feeding onto the higher algorithms is not drifting, has not lost linearity, or is not biased in any way. The other thing important to that, and of course, this comes with different terminology, is the fault descriptor or the features engineering. So these are the domains, these are the properties where some faults can easily be spotted, right? So we want to have an idea of how you guys are coming up with that to say this makes the diagnostic reasoner model work easier, right? And obviously within this, fault descriptors or features, it's important to understand what is the fault detection or severity estimation rules or logic within those features. That is being capped off right now by the different diagnostic models and reasoners that are going to be employed. So I'm just showing here a neural network that was developed by LR in partnership with some companies back in the 90s. So it's able to detect these different types of faults, right, with these different types of inputs, right? But it doesn't matter if you're using a pure data-driven, a physics-based approach, or a combination of both. We want to have confidence that the diagnostic reasoners involved have the right robustness, have the right repeatability, and accurately diagnosing or articulating, especially if you're fusing different fault modes. And of course, prognostics, as I've said, we're still exploring on the different verification and validation techniques here. But right now, the best we could come at is something statistical, right? Because it's very difficult to understand trying to capture all the different stressors and their effects, especially in a complex machinery. So this is work in progress for LR. Confidence in cyber resiliency, we've released a lot of rule sets talking about essentially embedded complex or integrated electronics. So we'll look at them on a component perspective, but also on a functional and systems perspective. So these are some of the domains that we consider within cyber resiliency, and human factors comes out on top, right? As we say, it's no use having a lot of tools, a lot of technology, but you really got to make sure that humans are part of that design or integration process. Obviously, data quality is very important. I mean, all of this, analytics require on good, high-quality data. The system architecture to always continuously get that data from one place to the next to perform the analytics and generate the insight is important. Hardware, obviously, some of the industries that we're operating in are pretty adverse, so you got to make sure that the hardware making that happen has been tested to those environmental or other dynamic conditions. Communication networks, you got to make sure that there's resiliency in the network, and if that data corruption does happen, there's some mitigation and remediation that the analytics could proceed, right? And of course, cybersecurity, system integration, and configuration management. What you will see here is obviously the analytics is a continuous improvement process, right? So a lot of these models do update themselves from time to time, and we want to make sure that there's a systems in place for keeping tabs of all of these updates so we understand its proficiency at any point in time. As a closing slide, ultimately, fault detection and diagnostics proficiencies are validated during parts removal, right? If you're saying that this is the condition of that part, these are the faults experienced that part, the simplest way to do that would be when you actually do the inspection or you do the maintenance or the overhaul, that whatever the analytics or the insight said, that is indeed the condition of that part. Prognostics is a bit more challenging than that because, as I've said, we can only estimate the different stressors. And then, some people, of course, are developing a lot of proprietary descriptors or features to capture the stressors and integrate them with the damage dimensions. But, the reality is there's not just one or two faults in a big asset, right? There's a lot of faults. There's a lot of failure modes that are happening affected by the same stressors in different ways. So trying to organize that into a system that's repeatable, that's robust, it obviously remains a challenge, right? But obviously in any of this, and again, our service is centered on trying to provide a level of uncertainty or certainty in the sense that we can assign sufficient confidence with the diagnosis and the prognosis. And with that, thank you for your attention.